Hi, in this chapter or section, we will talk about diffusive mass transfer at steady state. We are starting from this simplest of the mass transfer situations and will move to more complex situations in the following chapters. Little bit about the prerequisites for this module or for this chapter. Shown is the transport equation. We expect you to know how this was derived and what physical process each term represents. Now, to recap, this comes from conservation of mass. This entire equation is just a statement of conservation of mass. Here is the storage or the transient term, and this is the term due to bulk flow. Notice it has a velocity u. This term represents diffusion, and finally this one represents generation, which in the context of mass transfer has to do with either generation or depletion of species, typically from chemical reactions. Here we see how this chapter relates to other chapters in the mass transfer section of this textbook that we are following. So chapter 9 had to do with conservation of mass. And then chapter 10 had to do with the laws governing modes of mass transfer, like the Fick's law. In 11, we combined those two to get the general equation. Now, the general equation combines those two, but we're going to solve the general equation for special cases. So the simplest scenario is without bulk flow. So it's just diffusion. And an even simpler case of that is steady state diffusion. And that's what we're going to talk about in this chapter. We want to see qualitatively two situations when steady state is possible. Here is the general statement of mass conservation. Now, first we want to consider a situation when there is no generation. So if there is no generation, in other words, this is not there, so then the way we can reach steady state when change in storage is 0 would be something like this. In minus out should be equal to 0. And an example of that could be this dialysis tube, where the inside of the tube here we have high concentration of urea in blood, and then outside is the dialysate fluid flowing with a much lower concentration, closer to 0, flowing over here. So we have a concentration gradient from inside to outside. So urea will transport this way, but this can reach steady state. This transport through this membrane can reach steady state as we have a source, or we have urea coming in and then urea going out. So in and out balances, and then we can get a steady state. In another situation with generation, and in this case negative generation, we can see that we can reach a steady state from this equation with in minus generated is equal to 0. So we have in coming in and we have generated, but it's a negative generation, and so together it can lead to a steady state. So it's sort of in and generation, they match. And when can this happen? So here is a situation of drug delivery in tissue from a drug wafer. So as drug is coming in, it is also being metabolized, or it's being used up. So what's coming in can match what is being used up, leading to steady state. So those are just two situations where you can reach steady state. Steady state meaning change in storage is 0. Now let's look again qualitatively at two situations when steady state cannot be reached. In other words, it's going to be impossible to satisfy this equation with right hand side equal to 0. So first consider a simple soaking process where some fluid is constantly coming in. In order for this situation to reach steady state, this has to be satisfied because there's only coming in, no out term and no generation. We are doing the situation when there is no reaction or there's no generation term. So then this equation has to be satisfied to reach steady state, which of course is not possible because a positive term on the left hand side cannot equal 0. In another situation, that is simple drawing where let's say a fluid is constantly going out. Okay, to reach steady state, then this has to be true. There's no in term here, it's only out and 0, which is again not possible because again this out term, and even if you put in a negative term before that, this negative term cannot equal 0. Thus, these are two of the situations where steady state simply is not possible. Now notice, in both cases, this one as well as this one, they will reach the surrounding concentration eventually. This will be completely soaked and this will be completely dry when things will stop. That is a state we refer to as the equilibrium. We don't refer to that as steady state. Those are the equilibrium states that it reached.